Welcome to a lesson on breadth-first search. Before we begin, let's have a quick refresher on graphs. A graph is a structure that is composed of vertices and edges, where each edge connects exactly two distinct vertices. The edges in a graph can either be directed or undirected. An undirected graph has edges that can be traversed in either direction. On the other hand, a directed graph means that an edge can only be traversed one way. Now that we've had a review on graphs, let's look at the pathing problem in the context of mazes. Given this maze, we want to find a path from its entrance to its exit. How can we tell if there's a path from one segment of the maze to another? And for that matter, how do we know what that path is? We can use a traversal to accomplish this goal. A traversal allows us to look at all vertices in a graph and construct the path of how we got to each vertex. You can think of it as leaving a trail of breadcrumbs. Before we can do any operation on this maze, we need to convert it to a graph. We can do this by representing the intersections of the paths in the maze as vertices, and the edges as the connections between those intersections. The edges create paths between the vertices. In addition to our standard graph structure, our graph will have a couple bits of extra information in each vertex that are important for our traversal. First, we need a way to determine if we have already visited a vertex or not. This is important because if there's a cycle in the graph, our traversal may get stuck in a loop, never allowing us to exit. We will accomplish this by associating a color with each vertex in our graph. If we haven't discovered a vertex in our traversal yet, we'll color it white. Once we've encountered a vertex, we'll change its color to gray, and once we've fully explored all of the vertex's adjacent vertices, we'll color the vertex black. This way, if we encounter a non-white vertex in our traversal, we won't try and enqueue it to be processed multiple times. In addition to adding a color to each vertex, we will also give each vertex a distance value from the start. This will allow us to determine the length of a path. Finally, we will also give each vertex a parent pointer. This will be used to keep track of the vertex's parent in the breadth-first tree. The parent pointer keeps track of the vertex that enqueued a given vertex and is used to determine the actual path taken. Now that we've covered the additional bits of data we're adding, let's get into the algorithm. Breadth-first search allows us to traverse a graph by exploring the neighbors of a particular vertex, then expanding outward. If our graph was a tree structure, we can picture a breadth-first traversal as traversing each level of the tree. A breadth-first traversal results in two things: a breadth-first tree and the shortest path from the start vertex to each vertex in the graph. The breadth-first tree is constructed by parent vertices after a traversal finishes. By following the parents of each of the vertices, we can construct a path to get from the start of the maze to the exit. The most important aspect of breadth-first search that makes breadth-first search truly breadth-first search is how it keeps track of neighbors of the current vertex and explores them. This is accomplished by using a queue. A queue allows us to keep track of when items are discovered and systematically explore neighbors layer by layer because of the queue's first in, first out nature. As we explore a vertex, all of its undiscovered neighbors will be added to the end of the queue. We then explore the next vertex by pulling it from the front of the queue. Adding all of the child vertices to the end of the queue is what gives us the level-wise natures that breadth-first is built on. Here's the pseudocode for our BFS algorithm. We will begin by enqueuing our start vertex. Since the queue holds all discovered vertices, we will keep repeating until there are no more discovered vertices left. So, while there are still vertices in the queue, grab the next element in the queue and find all of its undiscovered neighbors. All of the adjacent vertices are considered neighbors of the current vertex, and are paths we can take. If we haven't already discovered a vertex, meaning its color is white, color it gray and add it to the queue to be further expanded. Before we add it, make sure to update the distance and set the vertex's parent to be the current vertex. Once all neighbor vertices are explored, remove the current vertex from the queue and color it black to signify that it has been explored. Once you are done, you will have a breadth-first tree. Let's see this in action in the context of our maze. We begin by enqueuing our start node, A, and marking its distance as 0. We then check if the queue is empty, find that it has an element, and then proceed to look at the element at the front of the queue. We see that the element at the front of the queue is A, so we grab all of A's neighbors, change their color to gray, and set their parent pointer to A, and finally set their distance to be their parent's distance plus 1. After we enqueue all of A's children, we dequeue A and color A black. In the next iteration, we again find that the queue is not empty and check the front of the queue once more. finding E this time. We check each of E's neighbors, A and F, and find that A is not colored white, so we skip it, only enqueuing and modifying F. Since there are no more adjacent nodes to E, we color it black and dequeue it. The next vertex we find in the queue is F. This time we have two undiscovered nodes that are adjacent to F, B and J. While it doesn't affect the overall result of our algorithm for BFS, we do need to define some order to process each node. In our case, we opt to use lexicographical order, processing letters earlier in the alphabet first before processing letters later in the alphabet, meaning that we process B before J. After we enqueue both adjacent vertices, we can see that they both point to F since F is the vertex that enqueued them. From this point onward, we can see that BFS will grow outwards along every unexplored path at an even rate, continuing to grow the breadth-first tree until we arrive at our last unexplored element, N. We see that none of N's adjacent neighbors are unexplored, so we dequeue N, mark it as explored, and check to see if there are any elements left in the queue. We find that there are no elements left in the queue, so the algorithm exits, returning the breadth-first tree. Say we want to know the path from the start node to the exit of our maze. How would we find the path to the exit? We can use the breadth-first tree to construct this path. By starting at our exit and following the parent pointers up the tree, we can construct a list of nodes to describe the path from the start to the exit. So what's the complexity of breadth-first search? Breadth-first search explores one vertex at a time. Each neighbor is added to the queue if and only if it has not been explored before. This guarantees each vertex is visited only once. Likewise, when traversing the graph, each edge will only be traversed once. This gives us an asymptotic complexity of O, E plus V, where E is the number of edges and V is the number of vertices. Thank you for watching. We hope you found this video educational.